All right, guys, welcome to Quarantine Statistics, Day 5. What we are going to be working on today is Example 5 in your packet with logarithmic regression. We're going to start on this problem today, but I actually don't think we're going to finish this problem today. We're going to do the first couple examples, and then we'll save that last one for tomorrow, probably. So, what I've done is you can see in the calculator, I put the data set in that it provided to me. This is a data set about the age of a tree in years and its corresponding height in feet. So in case it's been a while since you have seen logarithmic data sets, or if you're not quite sure you remember what exactly logarithmic means in terms of shape, I'm going to go ahead and graph this data. Now there is a graph on the page where you can graph it yourself. You can do that if you want, but don't feel like you have to. Since we're going through this example together, just kind of follow along is what we're looking for. So I'm going to go to Zoom and hit 9, and we will see the logarithmic data set graphed. This is a logarithmic curve. It is something that starts out fast, starts to slow down, and then eventually sees very little, if any, growth. You can see that in our data set here. Whenever we're going between points, we start at 6 and go to 9.5. Well, that's a gap of 3.5. Then we have another gap of 3.5. Then a gap of 3, so we're a little bit lower now. And then a gap of 1.5, so a little lower, and 1 again, and then only 0.5, another 0.5, a 0.2, and then a 0.1. You'll notice as those numbers go along in time, or as those numbers continue through the beginning to the end, the gaps between them start to get smaller and smaller. That's indicative of logarithmic data. With linear relationships, the gaps are always the same. With exponential, the gaps start small and get larger, and with logarithmic, the gaps start large and then end up getting small. So, like I said, this is what it looks like. It is that slow tapering curve, and what we are going to do is we are going to find the logarithmic regressions on the calculator today. So that's the very first question here after, draw a scatter plot, is find a logarithmic regression function. So I'm going to go into Stat and Calc, and if you recall, the option number 9 is for logarithmic regression. Even though it doesn't look like that, you'd think it would say log reg or something akin to that, but it actually says LN, which stands for the natural logarithmic regression. But it is option number 9 for logarithmic, so I'm going to hit enter there. And then I'll make sure my lists are good. And I end up seeing, first off, the standardized form for a logarithmic equation, which some of you guys have denoted y equals a plus blinks, but in reality is actually y equals a plus b times the natural logarithm of x. That's ln. You actually see ln on your calculator right here next to the 4 button. So I'm going to write this down. I'm going to move the calculator off screen for a second. So we have y equals a, and it told me in this problem that a is 6.1. 6.1 plus b, which is also 6.1, coincidentally, times the natural logarithm, or ln, of x. So in this problem, y is representative of my y list, height in feet, and x is representative of my x list, age of the tree in years. The ln, and I know I said this a minute ago, but I want to really clarify it, make sure you guys are aware. The L and the N are not variables. They are not values that we have to plug in. It is a logarithm. It is the term for the natural logarithm. And it is strictly a function on the calculator that we are going to put with whatever value of x that we are solving for. So whenever it asks how closely does this function describe the data in the table, then we can take a look at, you guys know it, the r squared value, which is 0.98. That is a fantastic r squared value. And we could also see from the graph that this is very descriptive of logarithmic data. It very much looks like a logarithm. D says, what is the average height of the trees at 1.5 years of age? So what we can do is plug that into our equation. So we can plug in 6.1, because we're solving for y, we're solving for the height. We want to know x, the average, or we want to know y, we know x, the age, 1.5. So 6.1 plus 6.1, and then again we hit this LN button. Sorry, let me put this on screen here. We hit this LN button right here, and then we are going to put in our x value, 1.5. Close those parentheses, and we get 8.57, or rounded to 8.6. And we find out that the tree would be approximately 8.6 feet in height after 1.5 years. We can do that again with this next problem, which says, what is the predicted average height of trees at 20 years of age? And then we want to know if the prediction is realistic. So let's plug that in. 6.1 plus 6.1 times the natural logarithm of 20, and we get 24.3 feet. So when we talk about, is this realistic, we want to know, is this plausible? We saw this a lot with some linear problems that we worked on whenever, there was one, the first one we ever did like this, I think, was with grades and a test. And we said, if you have a person that studies for X amount of hours, then they end up getting a Y grade on a test. And we said, can the equation go on forever? And we said no, because one, there's only so many hours you can study, and two, only so far your grade can increase. This is historically a huge problem with linear models of data, is because you can't just keep increasing the same always. But logarithmic models take care of that for us. They take care of that very slow increase once we eventually hit those very later on years, or those very later on amounts of time. So I would say this is realistic. I think this is a very realistic answer to the question. What we are going to do is work on F. When will the predicted average height of the trees be 11 feet tomorrow? Because that's going to kind of flip the script on us. That's going to want us to know y and solve for x. But there's going to be a little bit of practice that's going to have to go into that. So tomorrow we're going to learn how to solve a logarithmic equation for x, and we will solve this problem at the exact same time. All right, see y'all then.